We have the Sapphire group that's here. And how many of you have heard of the Sapphire group? Ooh, that's pretty good. We have Montgomery Childs and Dr. Michael Clarage. I first saw Dr. Clarage speak at a conference, Observing the Frontier in Albuquerque, New Mexico. And I was extremely impressed with Michael's talk and made a beeline for him and had a nice conversation with him. So I was able to meet him in person and started to understand more about the work of the SAFIRE Project and really felt their inclusion here at this conference was absolutely necessary. So it is my great honor to be able to provide their introduction. So SAFIRE, designed with multidisciplinary collaboration, replicates the atmosphere of the sun in a laboratory. I don't know about you guys, but I think that's pretty cool. All right, I'm glad I didn't have to say that. It's hot. Montgomery Childs is the program leader of the SAFIRE Project, founder of Aurtas International. He is the creator, chief scientist. He's also authored textbooks and has been a lecturer. He has 13 patents in the fields of machine control and plasma physics, holds a number of board certifications related to applied physics, mechanical engineering, statistics, and computational fluid dynamics. He's patented and prototyped advanced solar panels. He also designed a rocket to measure for atomic oxygen in the Earth's upper atmosphere at the request of the Canadian National Research Council. Pretty impressive. Dr. Michael Clarage is the SAFIRE astrophysicist. He has a PhD in physics from Brandeis University in Boston, studying the biological and statistical behavior of proteins. Dr. Clarage bridged the gap between astrophysics and the SAFIRE laboratory. He's researched binary pulsars, made discoveries in the areas of fractional calculus and chaotic systems, designed and managed the production of one of the first secure phone messaging apps for physician communication. His public lectures have shown many new ways to understand relativity and dimensions, metaphysics and biology, and how to include the idea of function in astronomical phenomena. A tremendous amount of astronomical data is needed to be reinterpreted to take into the account the influence of electric fields and currents, which have been largely ignored in astronomy. Plasma physics and key astronomical data from NASA and ESA then need to be coordinated in laboratory experiment. So my pleasure to introduce the SAFIRE Project.
Well, good afternoon. And this is my first experience coming to Holland. I want to say that it's a beautiful country. And the highway is so quiet. And it's very clean. The Stellar Atmospheric Function and Regulation Experiment. That's what SAFIRE stands for. The SAFIRE Project was created to answer the question, a question so eloquently phrased by Dr. James Ryder: why does the sun shine? The mandate to recreate the atmosphere of the sun in a reactor in a laboratory on Earth. To unlock the mysteries and learn from nature the most effective way to create self-organizing plasma and tap into and harvest the energy of the sun. But before we dive into SAFIRE, we want to familiarize you with two models of the universe: the gravitational model that so many of you are familiar with, and the electric sun. A
According to current theory, the Sun is a ball of gas so large that its internal pressure produces a continuous thermonuclear reaction. The power of the Sun comes from the Sun itself. These are the prominent features of the Sun. Every feature here poses a riddle the thermonuclear model cannot easily explain. This model of the Sun has been with us for about 100 years. Another model of the Sun has been taking form over the last 250 years.
In an electric universe, the heavens are not an empty vacuum. Vast electrical currents stream across interstellar and intergalactic space. They draw matter into a spiral vortex to form a spiral galaxy. The galaxy is lit by the stars strung along the current streams. Electric stars. In an electric universe, the Sun is a positively charged body in a negatively charged galactic environment. And if such is truly the case, then these features of the Sun are no longer riddles or anomalies. They are exactly what is to be expected. But the electric sun hypothesis has the same problem as the thermonuclear sun hypothesis. We've never been able to test either in a laboratory.
So with that, I'm going to see for Michael. He's going to come up and he's going to talk to you about the interstellar medium and many other things.
Thank you.
You're welcome, sir.
Hello, very good to be here. No monitor? See if you can get the monitor. Gravity versus electricity in the terms of how a star works. What's great about being here for a conference that's focusing on energy and energy production, the Sun, every star, is a perfect example of something that puts out an enormous amount of energy. And so we can learn from that. We can study how a sun does it, and then maybe there's aspects of that that we can learn from. Since the time of Newton, we have talked about forces as what changes the world. This is a very simple, elegant formulation which has fueled a lot of mechanistic science for hundreds of years. It's a very useful way to look at the world if you're a scientist. Forces cause change. It would be a much longer lecture to tell the story of how this chart came to be. Those are the forces that are considered in modern astrophysics. The first, gravity, is considered the king. Gravity is considered to cause everything else to come about. We then take into account the effect of magnetic fields, nuclear forces, the weak force. Why has the electric force been left out? I won't go into the why, but it has been. Electric fields, electric currents, not allowed. If you imagine the gravity model, I'll talk us through now the causation through the gravity model. We imagine space with dust, debris, and a lot of emptiness. But gravity is considered to be acting. It pulls together matter. That pulling together creates great pressure, great temperature, and eventually, boom, you get a star. Star is created. Some key aspects of this to highlight. One is the star is all alone in the gravity model. It is separate from the rest of the universe. It's on its own, burning its own fuel. It only came about because of some accident, that there just happened to be enough matter that just happened to come together. And that's it. The star in this model gets all of its energy from itself. Another drawback of this model, though, is that it has never been observed to actually happen in nature, and it's never been replicated in the laboratory. Another aspect of the problem here is that it violates the laws of thermodynamics, this model. So those are some pretty big strikes against it. What then would happen if we included the idea of electricity, electric fields, electric currents into the picture? It definitely changes the story. There's a term that a lot of us are wrestling with about how to call this. What do you call it when you include electricity? You can call it plasma cosmology. Some people refer to it as an electric universe. I don't know if one term is better or not. It is important to know that the Sapphire team were not associated with the Electric Universe group. We're a separate organization, which is fine. They do a lot of really good work. We do a lot of really good work. Let's talk through then what the story would be if we include electricity. What story could we tell about the origin of stars? Again, we have space, but now it's no longer empty. There is no such thing as empty space. Matter is permeated by electric fields and electric currents. That's our image for electric fields and electric currents that are in space. Plasma is perfect at conducting electricity. It's the best conductor that we have. And it naturally forms into rivers of current. It also naturally supports strong electric fields. These electric fields and currents naturally organize themselves and the matter that they go through. And there is no violation of any laws of thermodynamics. The matter can condense into a variety of localized structures, some of which we know about in the laboratory, such as plasmoids. Others we are learning about by studying the interstellar medium. And the picture is that then stars live along these currents, electric currents. The stars then receive their energy from the space around them, or better to say, from their relationship with the space around them. We still envision a center core, which is made up of a variety of elements, depending upon the star, the history of the star, or what the star's purpose is in the galaxy. That is, in the model, that's the positive pole. Think of an anode. And that's in an environment that is relatively negative compared to the positive. As was said yesterday, we often run into discussion problems when people fight over the word positive and negative. Maybe they're not the best choice of words. Maybe we don't understand electricity, but we can do some good physics by talking about it this way. So the surrounding medium is the cathode in this model. The star lives, again, inside of a larger electrical structure. The plasma will seek equilibrium. There's that separation between the plus and the minus. That creates a lot of motion, a lot of activity. Things try to come to equilibrium, but they don't. They can't. Just like you and me living here, you could argue we're trying to come to equilibrium, but we never do, right, until we die, and then we're in equilibrium. That striving to come to some equilibrium is what we see then, the byproduct of that is this immense amount of energy and light that comes from that struggle. To highlight again what I said before, in this model, the star is not creating its own energy. The star is, better to say, transforming energy. And that energy comes about through the star's relationship to the space around it, its relationship to other stars, its relationship to the galactic medium is the source of the energy. Also, we're starting to replicate a lot of these processes in the Sapphire library. When we got the instruction, okay, stars, atmosphere in a laboratory, that's not at all a simple ask, right? We're going to talk about a few of the results we have that we think means that we're starting to do that in concrete ways. The planets get their energy from the sun. The sun gets its energy from its larger world, right? We live in a hierarchical universe. There's some blueprint that's being manifested over and over and over that has to do with energy transformation. How do you transform energy from a star to a planet? Stellar energy is way too intense for a planet. Direct stellar energy would fry a planet, right? It would be gone. So how do you step it down? How do you bring that energy, solar energy, down to a level that a planet can use? Same is true with you and me. If you put us up into the magnetosphere, we would die. Too intense. How do you step that energy then down to a level that you and I can live in so we can have things like broccoli and hamburger and we can eat and we can get on? Help me, I'm going off script.
That's fine. You're doing fine. It's wonderfully entertaining. Yes, it was the broccoli part. Yeah.
Can you take over?
Sure.
Okay. Here you go.
This is how it works in the lab. Oh, I got a pointer. Thank you, Michael. That's how it works. Currently, energy production systems, Earth are secondary. Well, what Michael's saying, and he's going to get into this later on the interstellar medium, we decided to break up the presentation into kind of going back and forth between astrophysics, the interstellar medium, and what we're seeing with Sapphire. We're trying to draw a cohesive picture for our audience for the first time. So I'm going to skip over these slides here because we will be getting into this. Yeah, we don't need to see this. You guys, after conversations with you privately, this is a wonderful audience. So what I mean by that is we get into some talks where the audience are not into these types of technologies. So the idea behind it is, what if we could tap directly into the sun for our energy? And so we get into Sapphire energy. And what we're going to do is we're going to walk you through the reactor, because none of you, or many of you, probably have never seen the reactor and some of the tests that we've done. So let's see if this works. We're sitting in the heart of Sapphire. And Sapphire is based on the premise that the sun is a positively charged body in a generally negatively charged environment. The idea behind it is that electricity is the primal force in the universe. To do that, we create our sun, which is this anode, a positively charged body, in a generally negatively charged environment, which we get from these cathodes. And this is the chamber in which all the gases reside, and we watch quite phenomenal behavior, you might say. And have we been able to create the atmosphere of the sun? And the answer is yes, we have. That's a pretty brave thing to say. We held off for 2 years, and before we said anything, we had evidence, but it wasn't until this past year, and you'll see why, when we were getting transmutation of elements, that we were confident enough to make those kinds of claims. Okay, it looks like I got 2 slides the same here. Sapphire reactor. Okay, yeah, it's good. And this is the main Sapphire reactor. And on top we have a gimbal where we have probes to measure the plasma. We have antechamber, we have cameras, we have pumps, We have our main power supply. We've got resistors. We've got leak detectors. We have a large turbofan to cool the reactor down. And we even have a little fan to cool the resistors. So measuring energy. I don't know how many of you are familiar with thermodynamics, but this idea, you have a heat transfer, you have energy transfer. And if you have a pot of water, as an example, and you want to heat that pot of water up, it takes a certain amount of energy. You could use a candle, and it might take 2 hours to heat it up. And that candle represents a certain amount of BTU or energy that's going into that pot of water. Or you could use a blowtorch from the mine down the road. Well, if you have a mine here in Holland, I'm not sure if you do. And it might take 2 minutes. But the temperature of the water, let's just say, for argument's sake, reaches the same temperature. But the amount of energy that went into the same pot of water was very different. And so you have a rise in temperature. And that rise in temperature over time is a very key component to measuring how much energy is going into that system. A candle, obviously, it's not much. A blowtorch, it's a lot. So if the temperature climbs very quickly, you have, as I said, a good indication that there's a lot of energy that's there. So this is a moment when we first saw transmutation.
Yes. Hydrogen flowing. Yes. This is new. Okay, let's bring it back up. What do you want, the 20 tower? Yes, 20 Dory. 20 Dory said. Okay, try to control your discharge here. I'm supposed to vibrate where I want to be. Okay, so I'm saying that's going in now. Not now. We've got to bring the pressure down. Yeah. And restabilize. Bring the pressure down, bring your power down. Your voltage back. Bring your power back. Bring it back. Bring it back to, say, make it 5. Okay. Yes. Okay.
So what was that all about? That was the time, this year, we met in Toronto a year and a half ago because we had done a lot of plasma experiments, we had done a lot of measurements, and it was now time for us to go into what we call the higher energy plasma discharges. And the reason why we left them at the end is because, according to Walt Thornhill, Don Scott, and ourselves, we assessed it. We thought there may be risk that we could melt the reactor. And what was happening is when we introduced new gases and with a combination of other alloys, we watched the temperature of the reactor take off, and we were actually starting to melt the core. And we had introduced other gases later on that would actually have the opposite effect. We'll talk about that in a minute. So we have thermocouples. As you can see, we have a lot of instruments. We have IR cameras, we have UV cameras, we have optical spectroscopy, mass spectroscopy, voltage. We're measuring everything we can measure concurrently at the same time, and sometimes in picoseconds. And then we'll show you some overlay of various instruments that we have while the plasma is running, and we can show you what happens in the optical. At the same time, we can show you what's going on with the thermocouple, and as you can see, some of the energies in the optical that are going to show up. Michael's going to go over this with you. This is the same time that we start to see new elements appear. So in any case, what I want to talk about here is just the thermodynamics. So thermodynamics means that there's an energy transfer. And what we found was the original design, for 3 years, it ran exactly how we had designed it within the temperature frame with the fans and the cooling systems until now. And what happened is that the chamber was designed that once we reach 110 degrees on the surface with all cooling systems running at 100%, we knew that that's the maximum limit. We had to shut the reactor down because it was taking off on us. And we'd never seen that before until now. So this here, as I said before, is an overlay. I don't know if I can show it to you. Can you see a pointer? Okay, good. So what we have here is we have a bolometer, we have thermocouple, and what's it say, infrared camera. And these are the measurements that were taken. The one I want you to keep your eye on here is the thermocouple. Because this rise in temperature Well, we'll get into this in a minute. But in any case, this here is what we call an overlay. Okay? This is 1 day of experiment. So there's a full day. We run the reactor for a full day. It's not like something happens for a microsecond, then it disappears. We can run it, well, we used to be able to run it as long as you want. Oh, what happened there?
What is a bolometer?
It's like a total energy, it measures the total energy from radiation emissions and other energies, right from black body right through to some of the higher energies. It's kind of a relative thing. Ben, this video.
Hit the forward arrow. It's the bottom right-hand corner of the keyboard. Bottom right-hand, just hit the little forward arrow.
Oh, there we go. Perfect. So you can see the changes in the plasma as the temperature increases. And then we make some changes, and by the way, we're using the same gas composition through the whole day. We made some ratio changes, but basically. And this is when things got really, yeah, spooky is good. So that presented a bit of a problem for us, as you can see. It wasn't supposed to do that and had not done that in 3 years. So what did we do? How did we get there? Well, I want to take you on a bit of a journey here, I think. Oh, I'm going backwards. That's what the problem is. Give me a second. Okay, so this is the area. This is the region. So when you take a look at this curve rising, this is the temperature rise at the chamber over time. It was not supposed to do that over that time. It's about, maybe 30 minutes, if I recall. And what had happened, that means that the power settings on the reactor would have had to be at maximum. But we were only at 7%. So what we learned from this exercise down. The drop-off is after we shut it off, gives you an indication of how effective the cooling system is. This is a massive chamber. It's about 2,000 pounds. For you to heat up a 2,000-pound piece of stainless steel takes a lot of energy. It took very little. But it also means, too, that the cooling systems are very effective to bring it back down, but we could not stabilize it when it was running. Well, we couldn't stabilize the temperature. We could shut it down. So what does this represent? This represents another gas that, according to our physicists out of Los Alamos and Lawrence Livermore Labs that have been working with us since 2013, said this gas that we're using is going to be extremely reactive. And according to all the information that we had on this particular gas, we were concerned that we might actually blow up the reactor. But it had quite the opposite effect. It actually took energy out of the reactor and cooled down the core. And other gases that we used, which you would think are more benign, actually had the opposite effect. And what does that mean? It just means that the particle physics and plasma physics models cannot model what we're seeing going on here. It means the math is broken. It had the opposite effect. So going back and forth, his job was to predict plasma behaviors and explain why we're getting the plasma double layers, which no one has really been able to do. That didn't work, and ultimately when these results came in, he said there's something wrong with the experiment, and you guys are idiots, I quit. We said, yeah, but there's the results. So anyway, the math, it just means the math it can't get us that far. And we're convinced now, and you'll see later, we believe that we have to get involved with nuclear chemists as well as plasma physics, and we're going to have to develop a new math and you'll see why later as we go on. So, cooling the reactor. Okay, cooling the reactor. So think of the sun's atmosphere in this reactor, how hot it can get. It can get so hot, it will melt this stainless steel reactor. So we have to find a way to cool it down. And we have a turbofan here, that will suck 14,000 cubic feet of air per minute at 2 inches of water. Think of a jet engine, and it would suck all the air out of this laboratory in about 2 minutes. So all that air gets moved inside this shroud that we have here, in between the shroud and the actual reactor, to cool the reactor surface down. So we can run the experiment for an unlimited amount of time. Well, that's what I thought. Without melting. Mississauga. Without melting Mississauga. Okay? Mississauga is where the lab is. So computational fluid dynamics. Anybody familiar with this at all in the audience? A little bit, maybe? You know that it's pretty advanced. We use this technology now to design rocket engines and your car engines so that they don't overheat in a hot summer day and that they actually perform well in the wintertime, especially Canadian winters. So CFD, we just call it CFD. So we did a lot of modeling before we actually built Sapphire. We predicted very accurately how the reactor was going to work. And what you're seeing here is just basically gas temperatures, gas flow, under vacuum and radiation emissions. And we know that there's a difference between radiation emissions and radioactivity. The two aren't the same, by the way. You get radiation from the sun, but as it turns out, it doesn't create, from what we know, any radioactive materials or elements. Interesting. In any case, so we predicted the temperatures, and it worked very well, as I said, up until now. And the people on the team, it wasn't just myself, I do this, but there was Tommy Mello, who actually writes the code for CFD that NASA and others use. So these are pretty high-level people. And we all came up with the same result. Our physicist in Los Alamos, he did his model, I did my model, Tommy did his, and we came within about 50 degrees of each other, and we said, okay, look, we're ready to go, let's build a reactor. So what happened? Well, the design said that the reactor should be at 110 degrees on the surface for the thermocouple. That was the one thing that we could measure. We knew that it's like, this is go or no go. We reach that temperature, we got to shut it down. And that would have been with 100% power of 165 kilowatts. Okay? But we were at 12 kilowatts. And it gave us 100%, plus as you saw with the peak, we never did reach what they call a steady state. So we had to shut it down. Now we can control it and shut it down, but this is what was happening. And it has to do with what we think is nuclear chemistry, plasma physics. It's not just power going in and positive and minus charges. There's other things that are happening, and you'll see. So anyway, we have a candle that took 2 hours, our blowtorch 2 minutes, and we got to over 100% in 6 minutes with a candle. You see. So our calculations were off only by 93%. You're laughing. I've never been off by 93%. It's called being humbled, okay, by nature. But that's why our physicist, he had a meltdown. He really did. He had a meltdown. He just couldn't take it, and he ran back to Colorado, and we haven't really heard from him since. So we're making claims here that we can control. Sapphire can create, control, contain, and repeat any number of plasma regimes. For 5 years, Sapphire has performed exactly within the limits it was designed for, until now. This recent catalytic event was not predicted, and according to plasma physics, it should not have happened.
So these are double layers.
But it did.
See a little bit of something there.
This is calling into question our understanding of plasma physics and will require a new math
You definitely see the tufts in the UV.
and the collaboration of complementary disciplines to resolve.
There we are.
These recent catalytic events have not been observed before.
Okay, we're over pressure on that.
They're new and show the potential for a clean, energy-efficient reactor.
Forward, go to the second button to the left. Get on top. Stand by. Stand by. Temperature 310 minus 6 in case now you can go into.
So what we think may be happening, people say, we get on the internet and we go into some of the blogs and we watch what people are saying about our project, and people are saying they're getting LENR, they've got fusion, they've got this. We're not going to make any claims that we're getting LENR or that we're getting fission or fusion. We don't think that's what's happening, because fission typically means you're smashing the atom and you're smashing it apart. And fusion, obviously, is you're smashing them until they actually stick together, okay? And LENR, low-energy nuclear reactions, isn't, in our view, much of a description, except that they're getting energy from the system. And you'll see today, when we go through EDAX and some of the analysis, what we think may be happening, and we want to come up with maybe a new term. And for now, we're thinking maybe the term electronuclear resonance may be the cause for some of the responses that we're getting, the thermal responses and the other reactions. So it's the term that we're using right now, so don't tar and feather us and run us out of Holland because we used a term that's not used before. In any case, so we're going to talk about transmutation. It's a big word. It just really kind of covers anything that changes in the nuclear world. And
Okay, then we can take these things here. Put them in the position.
these are some of the probes that we use to bring into the plasma to do the measurements. We're measuring optical spectroscopy, mass spectroscopy, electrical characteristics all at the same time in the same point within the plasma. Those are optical and mass spec tubes. This is like a long 6-foot hypodermic needle, okay? And the gimbal allows us to go in and move anywhere around within the plasma to do delta measurements, do whatever kind of measurements we want. And in this area of the reactor, we have a still camera, we have our gimbal, which controls the position of the probes, and it's a long hypodermic needle. Think of it in that way, that we can take into the plasma and move it around. We have ultraviolet light cameras, we have infrared cameras, we have video cameras, high definition cameras, we have thermal imaging as well. With the gimbal, as I mentioned before, we can move the gimbal around, which allows us to move the probe anywhere around in this region. Which allows us to bring the probe right up to the anode itself, measure through the plasma double layers to measure the electrical characteristics, the optical spectra, and the mass spectra. And that way we can tell what elements, what their energy states are, and what the electrical energies are. So, we start off with this anode. We're not going to tell you what it's made out of, okay? We have patents that are working on. We believe in patents. We are capitalists, okay? And it takes money to fund projects. So this is what it looked like before. And as you've seen, it was running. And it's starting to melt. And that's when you hear me telling the guy, turn it down, shut it down. And before dropped out. And this is what it looked like after. So we said, okay. Now we've repeated this experiment, by the way. So we said, okay, let's get this thing out. Let's start doing some scanning electron microscopy and EDAX. And well, what's that? Well, scanning electron microscopy or microscope, many of you have heard of it. You can zoom right into, well, you can get really, really close, take a look at the structures of things. EDAX is energy dispersive spectroscopy. Basically, it's the electron that excites the elements that are there, and we can tell what those elements are. And this technology has been around for 30 years, and it's reliable. So this is myself and June in the lab working with the EDAX machine, and we're making certain discoveries. But what we want to do, I think maybe this may be the first time for many of you, is this is what the surface looked like after. And we're going to zoom in real time to give you an indication what a scanning electron microscope can do. This is not what it looked like before. This is pretty cool stuff. We get to play with all the really cool toys. My grandson has a field day with me. So we looked at this, and we started seeing structures on this ball. We didn't know how it formed. We have ideas rattling around in our brains as why there's a ball here, but it's not the only ball. There's many balls on the surface that are in there. And actually looks like, as you'll see maybe later, actually looks like it's growing out of the material. And so scanning electron microscopy, this is EDAX. So EDAX does an elemental analysis, and it breaks it out. And there's different machines. They do a kind of a color pattern to show you what elements are where. So these elements of calcium, cerium, lanthanum, carbon, and oxygen were not in there originally. That's what that ball is made out of. Now the ones that don't have any, aren't showing you any elements, basically are part of the base alloy materials that we're using. So that's part of our secret sauce. You know, they have, you know what a secret sauce is? Okay, anyway. So we zoomed in with SEM in other regions, and we took a look at what those, we had a number of new elements that showed up. So we have phosphorus, and we have silicon, and titanium, and oxygen, and magnesium, and calcium, and sodium, and potassium, and aluminum, and carbon, and calcium, and sulfur. And we're like, where did this stuff come from? So immediately we're thinking we got contamination problem, okay? So we ran other experiments, and we knew that these materials weren't in the chamber. We ran 3 experiments, and we're getting the same results. Some more, some less, but still we get these transmutations. So one of the guys involved in our team works for the United States Department of Defense. Now they've allowed him to work with us. They have certain policies where you can have someone like that work with us. And he said, Monty, look, we need to send this down to an independent lab that we use. So we sent our sample down, and they found the same elements that we found, plus 2 more. And it's EMSL Microanalytical in the US, reputable company, very big corporation, and this is basically what they do. That was risky for us because, as you know, I hear people talking about fraud and how people aren't honorable in their work. It's risky. We said, we're not going to go out and tell the world anything until we've had it validated, because it's just not good science. It's just bad. There's enough of that going on. So this is what they found. They found balls. Interestingly, their SEM is better than our SEM, but you can see the structures here. It was really quite fascinating to see. It's almost like some sort of tectonic formations that are in here. And when you look at it on the EDAX, you can see that the lanthanum is in between the cerium. And so we found another region, and we found titanium, chromium. Zn is that tin or is that zinc? What is that? Does anybody know? I forgot what Zn is. Zinc. Yeah, it is zinc. Right. Okay. Yeah, phosphorus and carbon. Now we didn't want our EDAX machine is not as sensitive as theirs is. They can resolve for carbon and some of the lighter elements. We see it there, but we know that there's a certain noise component with our machine, and so we wrote them off. So this is their analysis. This is what they found. But what's interesting here is we both found in the original material in here these holes, these vent holes, and how the material is being eroded, and where we're seeing the other new elements is in between the original crystalline structure. These look like, blobs, but in metallurgy we call this, a crystal. Okay, but there's holes in here. And why is that important? Well, because that material under the thermal imaging camera said that we did not have temperatures high enough. We only had 1600 degrees. This material should not have melted, but it did. And the quartz that was surrounding the stem should have melted, but it didn't.
Why?
Well, we're trying to ask the same question, okay? This can fry the gray matter, So we're just going to say we don't know, okay? if we don't know something, we know, but what we want to do is we tell you what we do know, and we'll tell you what we don't know. And that leads into where the kind of work we've got. We've got some work to do. So here's the distribution of some of the early elements where they found carbon, calcium, chlorine, and potassium. And the white regions that you see around here is some of the original materials. There's other materials that were in here too as part of the alloy. Okay, so alloys make up, like say if you had steel, you have carbon in there. If you have some other alloys like stainless steel, you might have nickel and other things, you see. So, so these elements here, this is not a part of the original material. What am I doing here? Okay, so periodic table, add a catalyst. So we add our catalyst, and this is what it returned. Now we have aluminum and silicon up here. We're writing those off because we know our probe is made of aluminum oxide. Okay, so we think that maybe that's where it came from. We don't know, but we're just going to take it off the list. But these elements right now, we can tell you, did not exist before, for certain. And, right, optical spectroscopy. Well, this is where Michael takes over now. And a lot of the instrumentation that we have in Sapphire, like the IR camera, the optical spectrometer, these are things that Michael would spec. And I did the engineering, we put it together. That's why we're a complement team. I love this work. He calls me his Padawan, because I'm not an optical spectroscopist, but I'm his oldest Padawan, you see. In any case, Michael, it's all yours, man. It is so good working with you.
Thank you.
It is.
You too.
Yes. This is one of my favorite instruments. This is called optical spectroscopy. And the technology dates back as far as Newton, from what we know. They took a prism, they put light through it, and it splayed it out in that beautiful rainbow color. What we've learned since then is that every element has a unique light signature when it gets excited. So we know what hydrogen in it has a very specific, you might say, elemental DNA in a way. So when we do this, we bring the light in from Sapphire through these fiber optics, through the probes. The light gets splayed out, the camera at the back captures it, and then it converts it into a signal that we see on the screen here. And I can tell you, this is sodium. This is hydrogen. This is argon. The cool thing about this technology is that it is extremely precise, zooming down to 0.0001 nanometers. That's a trillionth of a meter. So imagine looking at a meter stick and then stretching it out 1 trillion times. That's what we're doing with the light, and that is what's so amazing about optical spectroscopy.
49 is hydrogen. And then we've got 486, 427, and 391.
So 1 is looking line of sight.
Yes.
3 is looking just off the surface of the anode.
Okay.
And 4 is looking out further.
3 is...
Here's a little portrait gallery of some of the optical spectroscopy results as we're running different situations in the chamber. You can see they're generally more complicated than the image you just saw in the movie. Simple elements like hydrogen have simple spectra, but when you throw other things into a chamber and start lighting it up, the pictures become a lot more complicated. There's an example of hydrogen. That tall peak on the right is the famous hydrogen 656 line. That's what the chamber discharge looks like at this point. There's the hydrogen 656 line. There's another famous hydrogen line, the 486 line. But then we go to the regimes that we were talking about a little while ago, where we're seeing more interesting activity in the chamber, and we get, for example, something like this. That would be the discharge we saw during this spectrographic image. There's software that exists that can help you identify the elements that you're looking at. Like any software tool, it is not perfect. It makes its best guess, and then you as the researcher have to interpret the results. That's just one run of asking the software, hey, what do you think is inside of here? But there's a lot of lines, and they're not uniquely determined, meaning that if you see this large number of lines, there's really many different elements that could give you any one of those lines, right? So if you just see a line, you can't say for sure what element made it. You could have a list maybe of 30 elements that have that line that they could emit for you. So we're staring at this, hours and days and weeks, and then something starts to click after a while, like a Sudoku chart, which I don't do that, but I've watched people do it, and you can see they're thinking, and then something kind of like occurs to them, and they write in the numbers. So that line right there, that line right there, that line right there, they're triplets. They're each one of those is a triplet of lines. And so it would be really unlikely if there was some random collection of elements that somehow all produced that. So then you go back, you rerun the analysis, you look at the data tables of atomic emission lines, and you find that only manganese will give you that triple of lines, that triple of lines, and that triple of lines. You could, for any one of those 9 lines, there's many, many elements that would give you that one line. But if you see these three triplets together, it's basically a statistical impossibility that those somehow got put together by some other collection of elements. Zooming in there, you can see the relative heights of the lines, how high the peaks go. That's a wonderful branch of quantum mechanics. You would expect certain heights, relative heights between the peaks, depending upon conditions. And then what you're always comparing things to is the Boltzmann distribution or a thermal distribution. If it was just a hot oven, if you just had manganese in a hot oven, so it was all thermal activity producing that, you can predict the relative heights of those lines, which we see sometimes, but a lot of times we don't see that. We see different proportions in the lines, which means that it's not a thermally balanced condition in our chamber, which is no surprise to all of us. What all these other lines are, we still have a lot of work to do. Oh. Yeah, with the optical spectroscopy, for the elements that we are dealing with, so far we've not been able to. That's still a possibility going forward. But so far we haven't used it for that tool, for that purpose. And what I just talked through means that there's manganese in the atmosphere. In that discharge, there's manganese. We did not find any manganese on our anode, and we looked at the anode very carefully, right? We talked, I say it in one sentence. That took us like 3 weeks to admit that to ourselves, right?
Yes.
Yeah. So it's not at all an obvious thing. How could it be that there would be one element inside those layers, and other elements on the anode? In hindsight, you might go, well, of course, why not? Why wouldn't you expect that? But these aren't necessarily the thoughts you go into an experiment with. Those standing waves there are well known to a plasma physicist. They are denied by most astrophysicists as being possible, but they're called double layers. Is the term that has been used since the late 1800s. What's exciting about them is that there is no accepted explanation for how they arise, which is fascinating. 100 years of people studying these things, and there's, a half a dozen really good theories for them, but which of those half dozen, are they all right? Are they all wrong? But we know that plasma does it. Plasma does that. It will segregate. There's very strong electric fields between those layers. And it's that stationary electric field, that tension that's just staying right there, that's what basically all astrophysicists will tell you can't happen. You can't have that in cosmic plasma. It's been the mantra for 100 years. I can talk to you about that later. Yeah. If we then add to our picture, in the upper left there, sodium, oh, wait, where am I? Oh, manganese, yes. And then lithium shows up in the atmosphere also. Or is it sodium? We did the sodium in the atmosphere for that one.
We saw lithium too, but
Yeah.
sodium definitely, yeah.
Sometimes we see it in the atmosphere, sometimes we see it on the anode. Just to show you how strange these things are, I think I can tell this story. So we had decided to work with lithium to study it, but well before we put any in the chamber, we're seeing it in our chamber. And I did wonder sometimes if the chamber knew what was coming or something, right? It's just like...
I don't know. You can reach right out here now. You're an astrophysicist, so you can take liberty here.
All right. The transmutation of elements could lead one to realizing a practical application, which would be to do some remediation of the large amounts of dangerous radioactive material that we've produced as a society. And I will hand that over to Monty.
It's amazing because we weren't really looking at remediation of nuclear waste. Why would it even get on our plate to consider? But it just so happened a little bird in the U.S. said, Monty, I have some information for you, some studies that were done at MIT. And we started to look at this, and it's pretty amazing what they discovered under certain conditions. Anyway, I will play you another video. Videos are cool. Elemental transmutation occurs both in nature and in the laboratory, and is not a new phenomenon. Studies done at MIT have shown that when radioactive waste is exposed to hydrogen isotope nuclei, the observed decay rate of the radioactive material is effectively increased. Sapphire produces copious amounts of hydrogen nuclei that interact with other elements, creating self-organizing spherical plasma double-layer shells. Within these shells, electrons, ions, and molecules are trapped by powerful electromagnetic fields. This is where radioactive material would be exposed to the hydrogen nuclei to remediate the radioactivity of that material. So with the reactor, it's universal. We can put radioactive material in a sphere. It'll be positively charged anode. Or the base materials that we're using now and alloys, and combine those with a composition of gases where we get the catalytic events to occur. It's sophisticated, but in principle, it's actually quite simple. So the reactor, hydrogen fuel, then we carry on with, we put in nuclear waste. Obviously, it may need to be processed in preparation to go into the chamber. Electric power to initiate the reactions. It's a clean process. By the way, I don't know if I mentioned earlier, all the elements that Sapphire is producing are not radioactive. Now, there may be a transition, a short-lived transition, we're speculating, but we use Geiger counters, we use other types of instruments to go in to measure. We did not find any radioactivity. The elements that we're seeing are what we see in a periodic table. It looks like we don't have any isotopes. We had to confirm, though, but we're not seeing anything. And the final product for base elements, if you put uranium, radioactive uranium in there, ultimately it will devolve into lead. 206. okay, which is a little easier to deal with than some of the other things that we're burying in the ground or dropping into the sea to let our great-great-great-grandchildren deal with. And some of the half-life on some of this radioactive material is like 10 to the 7th. That's a long time. That's just a half-life. It'll still kill you. So finding a way to do this, what happens is that in Sapphire, while you remediate the nuclear waste, because it's a plasma, it's going to produce, it's going to boil water. It's very hot. So boiling water and turning a turbine is actually no big deal. That's been done. It's easy to do. And so now we get into the big picture. And Michael, you're back on. Man.
Back on. Thank you.
This is my favorite part.
Before it worked with the other thing. There, see it? See? One of the key ways of working that our team keeps coming back to is, what is nature doing? What's the natural way that things happen? If you've ever seen one of those photographs of the giant ITER magnetic confinement machines, nature doesn't do it that way. There is no situation out there where that's happening. And I think that's why we have not been able, as a community, to do it that way either, because nature does not want to do anything that way. I don't see, how do I put this? And I'm not looking for free energy. I'm not looking for energy out of nothing. What I see when I look at the world is that the universe has an enormous amount of energy that is constantly being transformed from one state to another in all of the most amazing ways that you could imagine. So I'm looking for the transformation of energy. And to look then at a large-scale picture of how is nature doing this already, we can look at stars and planets in the interstellar medium. This is a good, simple representation of a planet from an electrical point of view. Planets have enormous amounts of electric current coming into them and going out of them. It's not simple like a light bulb. No way. The currents are going in and out of the North Pole, in and out of the South Pole, and there's ring currents going around. This is just two sets of currents. We're up to, I think, like 6 or 7 that we know about now that are around Earth, Jupiter, Saturn. Oops, darn. Sorry. No. Maybe that. Okay. I'm sorry, we have to see that again. Yeah, so here's me drawing a planet.
He really does draw this fast.
I think you had to slow it down a little, didn't you?
Yeah. Monty, keep up.
And then we're going to take this planet picture, blueprint, if you will, design, idea, the way that nature is doing things, and we will put that into the larger world that a planet is part of. Namely, getting its energy from its star, its central star. Stars also have pole currents, ring currents. I'm drawing in some planets there. The planets all have their magnetic bodies, electricity coming in, going out. This pattern starts to appear if you draw it correctly, right? You start to see that there's some structure here that nature seems to be repeating. The magnetic body of planets is something I try to help my students understand. We see dots of light when we look at a planet. Like Jupiter is just a dot of light Oops. Jupiter is just a dot of light when seen with our eyes. But if we could see the magnetic body of Jupiter or Saturn, it would be larger than your hand if you hold your hand up against the sky. Different planets are made of different materials. There's no understanding really of why planets are made of different materials, but we do know that different planets are made of different materials. And then we're going to look at, well, let's place all of this into the interstellar medium. The interstellar medium we now understand is highly structured, and that was not known before 10 years ago. So let's take our star now. We're zooming out more. We see the star. Imagine all the planets around it. Keep that in your head. And we're going to place this into a larger world that the sun lives in, that the stars live in. We now know through direct data that there are filaments throughout the interstellar medium, and stars are only along those filaments. Stars are not randomly placed. They're placed like leaves on a tree. We also see these other things in there, which I'm making as blue dots, and you might see them referred to as protostellar cores or something like that. And whenever I hear the word proto, I know the person has no idea what they're talking about. They just need something to just put in place. Now, it may be that these other blue, I put them blue dots, are something else entirely. Why do they have to become stars? Maybe the stars are there to help these other things, right? We don't know yet. We don't know what all the roles these things play. There's a lot of organic molecules in the interstellar medium. It's one of those stories, you just get tired of reading them. Astronomers are surprised. Astronomers are shocked, right? All the organic molecules out there. Hundreds and hundreds of organic molecules. Sugars are out there. Amino acids are out there. What are they doing out there? If we look at just the inorganic molecules, though, elements, this is the list, the top 11. Okay, this is just by abundance. And this list changes, right, as we get more sensitive instruments. But here's the top 11 instruments. Part of what I do is study the interstellar medium, and this list is known to me. And after our set of experiments that you've just heard about, we're sitting there and we're going, wait a minute, I think I've seen this list before. Those are the elements that showed up. Those are the elements that we saw appear in our chamber. I don't think that's a coincidence. I think what we're looking at here is that the interstellar medium, in ways that we don't yet understand, is quite capable of making whatever molecules and elements it needs. It's not just some random collection, that those stars, the planets, the filaments, they all have functions up there in the galaxy. They're not doing nothing. It's an absurd idea to think that nature would organize such an enormous something that had no function. Makes no sense. So the interstellar medium can make whatever it needs or organize whatever it needs. The easiest elements that it makes and organizes are the ones that you're looking at there. And they are also the same elements that we see most prominently appearing in our chamber.
Take it, Michael. Whatever that's all about. Transformative technology. Transformative or disruptive. I hear people talking about we have disruptive technology. Our position on it is maybe a little more gentle in the sense that technology doesn't have to destroy economies. We don't believe they should. We believe that they should be transformative to help people migrate or progress from one level to the other. Disruptive technologies, well, they just don't typically work very well. So transformative technology works like nature itself. It considers all the factors, functional, economic, environmental, social, and political. It doesn't produce toxic waste antithetical to life. It doesn't attempt to bankrupt an existing system or put humans out of work. Why would you want to bankrupt your customer? It's transformative. It transforms. It doesn't trash. Capabilities. So capabilities, I'm going to go back to Sapphire a little bit, just to recap on some of the capabilities of our technology. We have more to show you yet. The capabilities, the creation of exothermic plasma reactions, creating a variety of spherical plasma discharges, containing, controlling, producing copious amounts of hydrogen, which is an interesting thing. Because we have, for those of you who are into these things, here we have 10.2 eV we've been able to confirm at extremely low energy settings. So that's, anyway, it's a fairly high energy state for hydrogen. Free protons through the hollow anode, and we have a number of patents on these things. Electro confinement of high energy photons, photon trapping. We've talked about this in other previous discussions, but I won't bore you with some of these things. What else do we have here? We have good instrumentation. Okay, what have we got? Optical spectroscopy, near ultraviolet light, polarimetry, remediation of radioactive materials, high efficiency production of electrical energy. Right, so the SAFIRE Project, what are we going to be focusing on now? So we finished with our mandate from the International Science Foundation, which was really to do an evaluation on the electric sun, electric universe hypothesis. And we said, once we got transmutation of elements, we said we're going to give you guys a clean bill of health. We will support the claim that the primal force in nature, we believe now, is electrical, is the electrical force. So a fully functioning laboratory for experiments, that's what we have. Energy generating reactor for producing clean energy, energy generating reactor for remediating nuclear waste. Harvesting potential energy. So that's our philosophy, that there's no real free lunch. When we talk about zero-point energy, we're not saying that doesn't exist, but it's going to take someone to make a device, and it's going to work at a certain degree of efficiency, and it's going to produce energy. There are a number of different technologies out there that all produce electricity, and they use heat and water. Sapphire would probably be a boiler, turbine type of reactor is what we see. And our final video, what are we going to be doing? Product development. Product development. The new technology is capable of releasing astonishing levels of energy. To convert this energy into usable electrical power is a relatively straightforward engineering project.
If it's a soft hose, but it's not vacuum rated.
An initial design for a power generation unit has already been completed. It is scalable, meaning the design will be virtually the same for the unit that powers a single house as one that feeds a large public utility. Using hydrogen as the fuel, the Sapphire plasma engine offers a potential for tapping into the catalytic plasma processes to produce abundant, clean energy. A number of patents have been developed, with more being generated. These patents represent a unique technology that can be applied to any number of scientific and commercial opportunities. Energy generation is all about efficiency. How one determines efficiency is much debated. But the Wall Street Journal factored in the cost of the fuel itself, the cost of production, the cost of damage that fuel and/or production does to the environment, and came up with a picture like this. Ultimately, nature itself shows us the most efficient way to do things. Sapphire will fit somewhere in this picture. The fact that the main fuel is hydrogen, the most abundant element in the universe, and that the process is clean and produces no negative side effects or waste products makes Sapphire a very attractive energy generating technology. And this is the Sapphire team. There's more than just Michael and myself. So some of the faces, some of the names that you'll recognize, it was actually Scott Mainwaring, who is a philanthropist who had been funding this project through the International Science Foundation since basically 2011, I guess, to some degree. And the way we structured our company, maybe this will be important for some of you here, it's a little different conference in that context. He said to us, Monty, we just want to know the truth about what's going on. Some billionaires like to buy hockey teams or football teams, and others like to buy boats, and some are really interested in science, and this is who Scott is. And he says, you guys can keep all the intellectual property. I said, well, that's really cool. Thank you, Scott. So I went out to the science team and I said, okay, guys, guess what? Let's start up a corporation, and you guys are all shareholders because they're the ones that are putting in the time. And we know how much scientists make. Well, maybe some make a lot of money, but often it's somewhat above the poverty line, okay? In any case, so that's what we did. So the scientists of the Sapphire team are actually shareholders in a new company called Orion Energy, which is an IP holding company. And, well, some of these guys are the core team. Some of them belong to the review team, which I don't know if we have. No, that's it. So there's a review team. So we have guys like Hal Puthoff. Somebody knows Hal Puthoff. And we have Dr. Donald Scott, Eric Davis, William Gardner, Walt Thornhill. What they do is they're like financial auditors except science auditors. You know, are you guys really doing science, and is it correct, and are you being straight up about it? So they do a review, and we provide monthly reports on the science and monthly report on our financials. So there's complete transparency. Except for one year, I couldn't find $167. But Scott told me it was because it was the beers I bought him when we were at the Hilton. So that's it. That's the Sapphire Project. We hope you enjoyed our presentation, and we'll be open to field questions when, I guess, when the time is right.
Later.
Yes, later.
Okay, later. Susan, I guess that's...
Beautiful job. Thank you so much. Thank you. Woo!